let's get some practice with naming cycloalkanes. When you see a cycloalkane, the one thing you always need to do is add cyclo to the parent. And I say that it is very easy to forget to add cyclo. So when you see that ring, maybe the first thing you can write is cyclo. And then count how many carbons are within that ring, and that will be the last part of your parent. So this example is 1, 2, 3, 4, 5, 6. So cyclohexane. When you have one group coming off of a cycloalkane, that carbon where that group is coming off is always going to be number 1.
So if you had more, it's still alphabetical, whatever the, like E would, like if it's, it would be your 1 and then you would go.
Right. So this is going to be isopropyl cyclohexane. Now, I talked about the geometric formulas. So this is kind of a hybrid geometric formula, condensed formula. Remember that with the geometric formulas, the hydrogens are implied. They're not explicitly written. This will come up more when we learn about chemical reactions of alkenes and alkanes, but just to give you an idea, like carbon number 1 here in the cyclohexane ring, there are 1, 2, 3 bonds shown. So how many hydrogens are on carbon number 1? 1. So that hydrogen is there. It's definitely there. It's just implied. So, you know, when working on experiment 11, you were asked to draw the complete structural formulas for the cycloalkanes, the condensed structural formulas, and then the geometric formulas. You know, that was all condensing that down. But the condensed structural formula for this structure, I'll write it up here, CH2, CH, CH2, 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 CH2. What's that? Oh, oh, gotcha. I thought you were saying something. A question. No big deal. But you can see these condensed structural formulas are kind of awkward to write. It's a lot easier to write the geometric formulas. Be aware, though, with the geometric formulas, those hydrogens are implied.
So is that when you start seeing, like, where, like for that one, for example, where they would just have that alkyl group, whatever, they would just draw like the lines, and they wouldn't have the hydrogens there?
Right. But we don't really get into that in this course, but you might have seen that in your organic earlier. Shane?
Does it matter if you go clockwise or counterclockwise?
With your numbering?
Yeah.
In this example, no. In future examples, we might see cases where going one way or the other results in a lower numbering scheme or a higher numbering scheme. So good question.
Whoever gives you the lower number.
Yes, exactly. Good question. Okay, so at the bottom of page 11, I ask you to draw the following cycloalkanes. And so I'll work a few with you, and then I want you to work a few on your own. 1,2-dimethyl cyclobutane. So with that one, you start with the parent. So this is the parent. Otherwise, it's going to be hard to kind of place your substituents, just like we did before with the branch chain alkanes. So your cyclobutane is here. And then I'm going to have methyls. Where you can number your cyclobutane wherever you want it to start. Doesn't matter. 1, 2, 3, 4. So this is my numbering scheme. I'm going to put my methyls here and here. Yours could be rotated. You know, yours could be at the bottom, to the left, pointing up. But like any structure in organic chemistry, there are many ways to write it. What matters is the relative location of these alkyl groups. Questions on that one? All right, let's go to this one. 2-cyclobutylhexane. So I'm going to say it again. 2-cyclobutylhexane. The parent name is what? Hexane. Is that in a ring? No. So it's not cyclohexane, it's just hexane. You're thinking of the cyclobutyl. We'll get to that in just a second. So just 6 carbons, 2, 4, 6. And then off the second carbon, you have an alkyl group called cyclobutyl. So cyclobutyl is just like cyclobutane, except it's missing a hydrogen. And it's connected to something. So it's just going to look like that. And then you would fill in your hydrogens. Questions on that one? All right, I want you to work these next two.
So I was like, kind of how, like on these, I saw how you like angled that one for cyclobutane, and like I was starting to, like when I was doing the homework, I kind of skimmed into chapter 1, and it talks about like how basically these are all like how the structures we were building, how they're all tetrahedrons, and so like they all kind of like, it's almost like they have a little polarity kind of like triangle, and so when we draw them to make them correct, we do kind of want to angle it like that where they're away from each other.
Right. I'm not a big stickler for having the correct angles, but the way I draw them is, you know, according to the tetrahedral nature of carbon. You know, even when you get into higher level organic chemistry classes, you'll see the wedges and the dashes, and we don't get into that. But, you know, there are some instructors who teach this course who are very particular about the angles, you know, but as long as you kind of watch how I draw them, and you see how they're drawn in the book and in the pink book, you'll be fine. Yeah. Okay, so isobutyl cyclopentane. You have just one substituent off your cyclopentane. So that's going to be on carbon 1. And so CH2, CH, CH3, sorry, CH3. Get into the habit of kind of changing up the way you draw your isopropyls and your isobutyls. You know, when you get comfortable with not writing it exactly the way it was on your note card or exactly the way you had it on your study sheet, that means you're really starting to master that alkyl group. Whereas if you can only recognize it written that certain way, you're kind of limiting yourself, because when you are on the, you know, taking an exam, for instance, and you need to recognize that as an isobutyl or an isopropyl, and you don't recognize it because it's not written that way, then it makes it harder. So, okay, 1,1,2-trimethylcyclopentane. So another cyclopentane, a little house, I say. So 1,1,2-trimethylcyclopentane. And so here's my 1, here's my 2. You could have had yours in a different orientation, rotated. That's fine, just as long as the relative location of the methyl groups is the same. All right, on the next page, I have cycloalkanes for you to name. I'm going to go through a few of these with you because there are little rules that you'll learn along the way. So this first one, what's the parent? Cyclobutane. And you have, off the first carbon, you have more than one group. So you're going to have to put numbers. Okay, so numbers are needed. 2 groups need numbers. Okay, so you have chloral and methyl. Which goes first? Chloro. So it's going to be 1 chloro, 1 methyl, cyclobutane. Now, if it was just one of those, if it was just chloro or methyl, it would just be chlorocyclobutane or methyl cyclobutane. All right. This next structure, the parent is cyclopentane. You want these substituents to get the lowest possible number. You could start numbering anywhere on this ring, but the best place to start numbering is where a substituent attaches. That's where you want to put your 1. So I can put my 1 here, and I can go clockwise or counterclockwise. If I go clockwise, this ethyl over here will be 3. If I go counterclockwise, it will be 1, 2, 3, 4. So just like your branched chain alkanes, it's going to take a little bit of practice to get your numbering schemes down. But this numbering scheme is better because it gives you the lowest numbering scheme for your ethyl groups. My 2.5 and 4-year-old, 4.5-year-old are into a thing where you ask them why, and because it's better. So everything is because it's better. So I think of this, because it is better to have lower numbering schemes. Because it's better. Okay, so the better numbering scheme here is 1,3 diethyl cyclopentane. Now, if you came up with 1,4 diethyl cyclopentane, that would be out of 3 points a half-point deduction. So not a huge deduction. You're definitely moving in the right direction. If you find yourself making little mistakes like that, eventually you won't make those mistakes the more you practice.
And maybe we're going to get to it. I don't want to jump the gun, but like if that wasn't an ethyl on the other side of it, and it was the same scenario, does it matter? Because it would change like the naming. Like, let's say you had an OH on that side, a red one is instead.
We will get to that on this next one. So yes, you're right on the money. Okay, on this next structure, the parent is cyclohexane. And if all you can do in the beginning when naming these cycloalkanes is identify the parent, that's okay. Take baby steps. Okay, so on this cyclohexane, we have what is this one? Isopropyl, good. And we have methyl. We have a choice. Who is going to get 1? Who's going to get the number 1? Isopropyl is going to get the number 1. Why?
It's better.
It's better because it's better. That's right. Yes, because it's better.
You should have never told me.
I know. Just these sweet little voices. Because it's better. What? Why did you hit her? Because it's better. So, the lowest number goes with the one that goes first alphabetically. So, 1 isopropyl, 3 methyl cyclohexane.
Well, you always end up in a scenario like that, or like say 2 was hydroxy. So then you wouldn't be able to do it, or would it just not happen like that?
There are molecules that exist like that. We try to keep the relative
We won't see anything like that.
complication. You know, I mean, if there is one with 3, it might be the counterclockwise versus the clockwise type of numbering scheme. But we'll go over some more examples. There are certainly very complicated organic molecules out there. Your drugs, for instance, like I could not begin to name them. You know, they're on some chemical drawing software that we have. They will generate names for your really complicated ones. Even those can be incorrect sometimes. So, but yeah, we don't make it too complicated for you. Like this next one, maybe this is getting at what you're asking. So with this cyclopentane, so before you get overwhelmed with numbering and, oh my gosh, I have no idea where to start, just put the parent down. That, you know, it gives you some confidence to move forward. At least I know the parent. I can, you know, maybe I can get half more point or maybe another point. But putting the parent down will help you tremendously. Now, we have 2 groups of substituents, so I can number it 1, 2, or I can number it 1, 2. And this kind of goes back to what you saw with the branch chain alkanes, where you have, if I go with the uncircled numbering scheme, it's going to be 1, 1, 2, versus, 1, 2, 2. So when you have numbering schemes face off, the numbering scheme that is the lowest always wins. So this is going to win. So then I'm going to go through and list in alphabetical order. So I have, and some, you know, in the beginning, just write all over your structures. So you have ethyl, fluoro, and methyl. Which comes first alphabetically? Ethyl. So we're not going with the circled numbering scheme. We're going with the uncircled numbering scheme. So that's going to be 2 ethyl. So even though it comes first, it doesn't have the lowest number. So 2 ethyl, and then what comes next? 1 fluoro, 1 methyl. Cyclopentane.
That's what I was basically talking about.
Yes. So
So you don't have to go 1, 2, 3, whatever. Alpha overrides the.
right. Okay, so what about the next one? What's the cycloalkane? Cyclopropane. Good. And then off cyclopropane, I have 2 groups. I have methyl and T-butyl. So it really, when you just have a cycloalkane with 2 substituents on, you know, it's a battle between alphabetically who will get the first number when you have 2 substituents. So you have B versus M. So B is going to get the number 1. So it's going to be 1 T-butyl, 2 methyl cyclopropane. All right, so work on the last one. Okay, so what'd you come up with for this last one?
1 amino, 3 nitrocyclopentane.
1 amino, 3 nitrocyclopentane. Good. So we're going to stop here for lecture content. I'm going to go back to your experiment number 11. Remember those questions? And if you don't have experiment 11 with you, you can just copy this down onto another sheet of paper. Yeah, it will make a lot more sense. All right, so number 1, this question, 66H14 has 5 isomers. We had answered this question in lecture, but anytime you're asked to draw isomers, start with your chain of 6, go down to your chain of 5, and then go down to your chain of 4. With these isomers, you'll find that you have 2 for a chain of 5 and 2 for a chain of 4. So that's 2 plus 2 gives you 4 plus 1 gives you 5. So that's all the 5 isomers. So practice from tonight's lecture, going through and putting down the isomers and the names. Notice that this is the condensed structural formula. So I'll do this first one with you, the easiest one. So what's the name of that guy? Hexane. So hexane, you only have one chain of 6. So then you've gotten 4 of the 5 isomers done. You just need to do the other 4 and name them. The key to making sure you don't duplicate structures is to name them. So, if you find yourself drawn in a funky way, and then you name it, you find that you've just drawn the same structure twice. So, but you can refer back to your notes to get those answers too. All right. Now, this is a good kind of way to gauge you if you've been paying attention tonight. I'm not real big on putting people on the spot, so I'm joking, but hopefully you'll be able to answer this relatively quickly. Is cyclopropane an isomer of propane? No. Why do you say no? It's got less hydrogens. Very good, because remember that this CnH2n, that's for your cycloalkanes. For your straight chain alkanes like propane, it's CnH2n plus 2. So this is your So you can see that a cycloalkane is going to have 2 less hydrogens. So the answer is no. Different number of hydrogens. Questions on that one? All right, question 3. Draw the structures of 1,1-dimethylcyclopropane, 1,2-dimethylcyclopropane. All right, so cyclopropane, what's that geometric? It's going to be a triangle. I heard it. Yes, good. Triangle. So this is 1, 1, and then 1, 2. Would look like this. Is it possible to have 1, 3? Right. So it's not going to be 1, 3. You said it. It's going to be 1, 2. So no is the answer. Does that make sense to everybody? All right, this question here is 1,1-dimethylcyclopropane an isomer of cyclopropane. Try to do this one as quickly as possible. Imagine this is a multiple choice question and you have a lot of structures to fill out on your exam. What's the quickest way to go about?
Count the carbons.
Count the carbons. Excellent. So how many carbons in cyclopropane?
3.
3. How many carbons in 1,1-dimethylcyclopropane? 3 plus 1 plus 1. So 5 total. So 5, they're not going to be isomers. So no. Different number of carbons. So very quickly, counting carbons just from these complicated names can tell you so much about whether they're isomers or not. So that shortcut hopefully will save you a lot of time and frustration instead of getting bogged down and drawing the structure. And we didn't even have to draw the structure. We just counted them up.
And so the other way, like if, for example, on the test they have like a chain or a branch, like a straight chain or a branch chain, and then you have a cyclo, you know from the get-go that they're not the same isomer because you lose hydrogens with the cyclo.
Right.
So you count them.
Exactly. Yes. Okay, the last one is 1,1-dimethylcyclopropane, an isomer of cyclopentane. Yes. They have the same number of carbons. So you have 5 carbons with cyclopentane. With cyclopropane, you have 3, and then you have plus 1 plus 1. So yes, they do equal each other. So yes, same molecular formula.